This is problem 4-31M. It's on page 234. For the shaft shown in figure P4-31, compute the angle of twist of pulleys B and C relative to A. The steel shaft has a diameter of 35 millimeters throughout its length. The torques are T1 is 1500 newton meters, T2 is 1000 newton meters, T3 is 500 newton meters. The lengths are L1 equal 500 millimeters, L2 equals 800 millimeters. You should definitely reference the figure. I will not draw it again on my board here, but I'll just trust that you'll go and look at it. I'm going to jot down all the given stuff. T1, 1500 newton meters. T2, 1000 newton meters. T3, 500 newton meters. This is a steel shaft. The length L1 is 500 millimeters, which is 0.5 meters. L2 is 800 millimeters, so that's 0.8 meters. And the diameter of the shaft is 0.035 meters throughout. Okay, so here's the solution I'm going to use. The angle of twist will be just TL over GJ. That's my general equation for calculating the twist angle. Okay, so let's work on this a little bit. For example, let's work on the polar moment of inertia J. J is pi d to the fourth over 32. So that's pi over 32 multiplied by 0.035 meters to the fourth power. Plug that into your calculator, you get about 1.4732 times 10 to the negative seventh, and it has units of meters to the fourth power. Now, the torque between A and B, what is that? Well, if you look at the figure, they're listed as T1 and T2. And since T1 has a load of 1500 newton meters on it, then that means that whole section, I'm looking at the figure here, from A to B carries a load of 1500 newton meters in that section of the shaft. So what that means is that the torque between A and B is just T1, which is 1500 newton meters. So if I want to figure out how much twist there is between A and B using this equation, then I'll need the torque in that section, and here it is, 1500 newton meters. Of course, the length is, as shown here, it's L1. So let me call this theta AB, just the angle of twist between A and B, given the amount of torque applied to that section. Anyway, that would be TAB multiplied by the length between AB, which of course is just L1, that's the same thing, divided by G. Now we need G for steel. If you go look it up in your book, you'll find that it's 80 times, let's put steel here. Basically what this tells us is that the torsional modulus is 80 times 10 to the ninth pascals, or in other words 80 gigapascals. So that's what the information about steel gives us. J we've calculated, I'll just write it down. Notice it's the same along the entire length of the shaft, so we don't have to recompute it. Anyway, so the torque AB is 1500 newton meters. And let's see, the length between AB was L1, which is 1/2 meter, divided by 80 times 10 to the ninth pascals. And then J, which is 1.4732 times 10 to the negative seventh meters to the fourth. Now, a pascal is a newton per meter squared. So there go the newtons, they're gone. We've got meters squared in the numerator, and in the denominator of the denominator we have meters squared. These meters squared could just the same go to the numerator. That's essentially where they are. Now we have 1, 2, 3, 4 meters, which cancel with these 4 meters. So we end up with something that is dimensionless, which is what we expect because this angle should come out in radians, and radians are dimensionless. So plug in all of that into your calculator, you find this is about 0.0636 radians. And if you convert that to degrees, that comes out, well, I didn't do that yet. I'll worry about that later. So this is the relative twist between A and B. Now let's take care of the relative twist between B and C. Well, now we need to know the torque carried in that section. You should be able to see that that torque would be 500 Newton meters, because you go from A at 1500 Newton meters to B. Okay, that section has to carry 1500 Newton meters. Once you get to B, a torque of 1000 Newton meters is subtracted from the 1500, so that leaves you with 500, which is balanced at the end. So it makes sense that you would have 500 Newton meters for the torque between B and C, and then you need the length between B and C. Well, that's just the 0.8 meters, that's L2. The torsional modulus is 80 times 10 to the 9th pascals, and then finally J is the same throughout the shaft, so 1.4732 times 10 to the negative 7th meters to the 4th. Of course, the units go away like they did before. They would have to, and we'll end up with radians. So this comes out to about 0.0339 radians. Okay, now notice these are relative angles. These are the angles between those two points on the shaft. Now the angle at B is pretty straightforward. Theta B, that's the angle that B would twist relative to A. Well, that's just theta AB. So that's just 0.0636 radians. And if you can convert that to degrees, it comes out to about 3.64 degrees. Okay, so there's the answer for the first question. The next question is, how much does the last element at C twist relative to A? Notice that both B and A are twisting in the same direction, so they would add. So you'd have the twist from A to B plus the twist from B to C, and if you add these two together, you would have the twist of C. When I did that, 0.0636 plus 0.0339, I got 0.0975 radians, which is about 5.59 degrees. So there's the result. So basically the first element twists by about 3.5 degrees, 3.64. The second element twists by another 2 degrees or so, so about 5.5 degrees or so, a little more.